So in the previous lesson, we looked at how to find the root or solution to a single equation using the fixed point iteration method. And in that particular lesson, what we did was, given a root finding problem of the form f of x equals 0, what we did was to transform this root finding problem into a fixed point problem of the form x is equal to g of x. Now the form x is equal to g of x was so important to us simply because we could have various forms of x is equal to g of x. However, we needed to find x is equal to g of x such that the absolute value of j prime of x was less than 1 at x equals x naught. So this condition needed to be satisfied. Now in this lesson, we are going to extend this same concept to system of nonlinear equations, or better still, functions of several variables. So given a system of nonlinear equations of the form f1 of x1, x2 through to xn equals 0, f2 of x1, x2 through to xn equals 0, and then fn of x1, x2 through to xn equals 0, where for all I is less than or equal to n, such that fi is a nonlinear function of the components x1, x2 through to xn. How do we find the solution or the roots to this system of nonlinear equations? So similarly, what we are going to do is we are going to transform each of the root finding problems here into fixed point problems, so that we have x1 equals f1 of x1, x2 through to xn. We have x2 equals f2 of x1, x2 through to xn, and then we have xn equals fn of x1, x2 through to xn. Now remember that in the previous lesson we made a point, and the point was the form x is equal to g of x was not unique. The form x is equal to g of x is not unique simply because we could have various forms of x is equal to g of x. Now for us to be on the same level, or better still the same page, a possible arrangement will be given in the problem, and we may need to use that possible arrangement to arrive at the root or the solution to the system of nonlinear equations given in the problem. Now also in this lesson, we are going to learn how to find the roots or the solution to a given system of nonlinear equations using the Jacobi iteration method as well as the Gauss-Seidel iteration method. However, for faster convergence, then you may resort to the Gauss-Seidel approach. So let's take our very first example. So in our first example, we are going to solve the nonlinear system f of xy equals 0, given that f of xy can be transformed into the fixed point problem, that is g of xy equals xy equals x squared plus y squared plus 8 over 10, and then xy squared plus x plus 8 over 10. Now starting with an initial guess of x naught equals y naught equals 0, we are going to solve this system using first of all the Jacobi iteration method, and then secondly the Gauss-Seidel iteration method. And then we are asked to perform exactly 4 iterations, leaving our answer to 6 significant figures. So how do we solve this problem? So we are given an initial guess, that is x naught equals y naught equals 0, and also you realize here that we are given a possible arrangement in the problem. Now this is given so as for us to be on the same page. So this is the possible arrangement that has been given. Now in a case where the possible arrangement, that is g of xy, is not given, then it means that you need to find the possible arrangement, and then you follow that to solve or to find the solution to the given non-linear system. However, in this case, since the possible arrangement has been given to us, then we may just follow that to find the solution to this system. So notice that we are solving the root or solution to a system of nonlinear equations, or better still functions of several variables. That is why this time we have g of xy. So first of all, we are going to solve using the Jacobi method, the Jacobi iteration method. So we have the initial guess x0, y0 to be equal to 0. So quickly, let's start off with the first iteration. Let's perform the first iteration. So for the first iteration, that is, we are going to find the values of x1 and then y1. So for x1, we are going to have, using this same formula for x, we are going to have x0 square plus y0 square plus 8, all divided by 10. So we have x0 to be 0, so 0 square. We have y0 also to be 0, so 0 square plus 8, and we have this all divided by 10. So this is simply 8 over 10, and then you realize that when you compute this, you have 0.8. So this is the value for x1. Now let's move on to y1. So for y1, we also have the formula. Let's first of all pick the formula, that is x0 times y0 square plus x0 plus 8, all divided by 10. So that is also equal to, we have x0 to be 0, y0 to be 0, so 0 square plus 0 plus 8, all divided by 10. So we have 0 plus 0 plus 8, that is 8 over 10, and then this is also 0.8. So this is the value of y1. So at the end of the first iteration, we have x1, y1 to be equal to 0.8. Now let's move on to the second iteration. So for the second iteration, we are going to find x2, y2. So we are going to have x2 to be equal to x1 square. So the value for x1 is 0.8. So we have 0.8 square. Okay, that is from here, plus y1 square. So 0.8 square plus 8, all divided by 10. When you compute this, you are going to have 0.928. Remember that you are supposed to leave our answers to 6 significant figures. So this is going to be the value of x2. Move on to y2. For y2, we are going to have x1, so that is 0.8 times y1, that is also 0.8. So we have the square of it, plus 0.8 plus 8. Okay, all divided by 10, and that is also going to be 0.931200. This is the value of y2. So at the end of the second iteration, we have these two values, 0.928000 and then 0.931200 for x2 and then y2 respectively. Now let's move on to the third iteration. For the third iteration, we are going to have x3 to be equal to, so we have this value is for x2. Okay, so x2 squared plus y2 squared. So x2 is 0.928, so the square of this, plus y2 square 0.9312 square. Now I'm just leaving out the zero so that we can at least make some space for ourselves, but then in the final answer, make sure you have the zeros attached to the values in here. So we have 0.928 square plus 0.9312 square, and then plus 8, so all divided by 10. And then we are going to have x3 to be equal to 0.97 2832. Okay, 0.972832. That is the value for x3. We move on to y3. We are going to have x2, which is this value. Okay, 0.928. that is for x2 times y2, which is 0.9312 square plus x2 0.928 plus 8. Okay, all divided by 10, and that will also be equal to 0.973270. 0.973270. So this is the value of y3. Now let's move on to the fourth iteration step. Okay, the fourth iteration step. So to the fourth iteration step, we are going to have x4, that is equal to, so it's going to be x3 square plus y3 square plus 8. So we have x3 to be 0.97282832. So we have the square of it, plus that of y3, that's 0.973270, also square, plus 8, and we have this all divided by 10. When you compute this, we are going to have 0.989366. So 0.989366. And then also for y4, we are going to have x3, which is 0.972832. Okay, so times y3, which is 0.973270. So we have the square of it, plus x, which is, that is x3, which is 0.972832, and then plus 8. We have this all divided by 10. So for y4, we are also going to have, that is after computing this fraction, you have 0.989435. Okay, 0.989435. So after 4 iterations, the approximated root of the given system of nonlinear equations, that is using Jacobi iteration method, is, we have x4, y4 equals 0.989366, and then 0.989435. So now let's solve this same question using Gauss-Seidel iteration method. So also we have the initial guess x0, y0 to be equal to 0, and then we have the possible arrangements. We have x to be equal to great. So what do we do? Let's perform the first iteration. So for the first iteration, we have x1, that's basically going to be x0 square plus y0 square plus 8, all divided by 10. So since we have x0, y0 to be 0, we are going to have 0 square plus 0 square plus 8, all divided by 10. This is equal to 8 over 10, and thus we have 0.8. So this is the value of x1. Now for y1, instead of putting in the value for x0, what we are going to do is, because we are doing Gauss-Seidel iteration method, now you remember we did this in linear systems, and so what we are going to do is we are going to update the records of x using the new x value that has been obtained. So instead of putting in the value of x0, we are rather going to put in the value of x1. So here we are going to have the new record, the new value, or the updated value of x, which is 0.8, times y. We have the updated value for y, or the value for y that we already have is y0 equals 0. So we put in here 0 square plus updated value for x is 0.8 plus 8, all divided by 10. So what we are saying is that for Gauss-Seidel iteration, we always update the values of x and y using the new values that we obtain. So here we have x1 to be 0.8. So instead of putting x0, that is 0, we are rather going to put in the value of x1, which is 0.8, which happens to be the updated value of x. So when you do this, this part goes to 0 because of the 0 here. So we have 0.8 plus 8. So that is 8.8 divided by 10. And that is going to give us 0.88. So this is the value of y1. So now let's move on to the second iteration. So for the second iteration, we have x2 that is equal to, so we are going to use the new value of x, which is 0.8. So we have 0.8 square plus new value of y, which is 0.88, the square of it, plus 8, all divided by 10. Now this is going to give us 0.941440. Now for y2, we have y2 equals, now looking at the formula, that is xy squared plus x plus 8 over 10. So the x value, you are going to use the updated x value, which is 0.941440 times updated y value, which is 0.88. So 0.88, and then we have the square of it, plus updated x value 0.941440 plus 8. We have this all divided by 10. When you compute this, you are going to have 0.967049. 0.967049. Now notice that for the first values, or the first iteration step, you can put this value in 6 significant figures. That is, you can add 5 zeros here and then 4 zeros here. Okay, so let's move on to the third iteration. So for the third iteration, we have x3 that's going to be equal to, remember that this was x squared y squared plus 8. So we update with the recent value, or the most recent value of x. So that is this one. So 0.941440, we have the square of it, plus most recent value of y, 0.967049, square plus 8 all divided by 10, that is equal to 0.982149. Now 2y3, that is also equal to, also remember that it was x times y square plus x plus 8 over 10. So x most recent value, that is what we've just found, 0.982149 times most recent value of y, that is this one, 0.967049, so the square of it, plus most recent value of x, 0.982149, and then plus 8 all divided by 10, and this is also 0.990064. Now let's move on to the fourth iteration. Now to the fourth iteration, that is x4. x4 is equal to the most recent x value, that is 0.982149, 0.982149. We have the square of it, most recent y value, 0.990064, 0.990064 also squared, and then plus 8 all divided by 10, and that is also equal to 0.994484. Now for y4 is also equal to, so most recent x value, that is 0.9944 4484 times most recent y value, that is the same value here, so 0.990064. we have the square of it plus 0.9944, that is the most recent value for x, and then plus 8. Okay, so plus 8 and then all divided by 10. Now this is also giving us 0.996930, 0.996930. So after 4 iterations, the approximated roots of the given system of nonlinear equations using Gauss-Seidel iteration method that is corrected to 6 significant figures is also given by x4, y4, and that is equal to, we have 0.994484, 0.996930. Now looking at these two sets of values, that is the roots obtained for Gauss-Seidel iteration, which is this value or this set of values, and then that's obtained for Jacobi iteration, that is this set of values. Now you realize that this set of values are approaching a particular root. You realize that they are very close to a particular root, and that root is xy equals 1, 1, and this happens to be the actual root of the given system of nonlinear equations. This happens to be the actual root. Now, as I said earlier on, you realize that these two values, x4, y4, are getting closer to the actual root, which is 1, 1. Also, for these two values, x4, y4, you realize that they are also getting closer to the root, which is 1, 1. Now, comparing these two sets of values that is obtained as a result of Jacobi iteration and then obtained as a result of Gauss-Seidel iteration method, you realize that the values for the Gauss-Seidel iteration method are much closer to 1 as compared to the Jacobi method. Now let's do the comparison. So for Gauss-Seidel you have 0.994484 for Ex1, okay, 0.994484. However, for Jacobi you have 0.989366, okay. Now also for the Y part, for Gauss-Seidel you have 0.996930, 996930. Here you have 989435. So you realize that the values generated or obtained as a result of Gauss-Seidel iteration is much closer to the roots 1 as compared to the values obtained as a result of Jacobi iteration method. So from this we can conclude that Gauss-Seidel iteration method converges faster as compared to Jacobi iteration method. And in fact, that was the same conclusion that we made when we dealt with linear systems considering these two iteration methods. So that's it for today's video. Thanks for watching, and I'll see you in the next video. Bye bye.